Welcome everybody to Integrated Math 3. In today's episode, we're going to be discussing chapter 9.1.2, which is called The Screamer. Now, of course, the screamer isn't exactly in and of itself a mathematical topic, but we're going to use it, this Ferris wheel type ride, as a means to show you what we're supposed to show you as a concept in this chapter here. So I'll go and read the first little bit for you. If you want to fast forward through it, it's no big deal. If you want to pause and read it yourself, feel free to do so, and then just go and skip to the next portion here. But basically, it starts off with hurry. The line is getting too long. We have Antonio and Renee. They're racing to get on the screamer. It says it's only been open for one day, but it's already the scariest ride in the park. I really want to get on, and before all the summer stuff. Okay, so it says Antonio whistles as he screeches to a halt in front of the huge sign that says "Welcome to the Screamer, the scariest ride on Earth." The picture on the sign shows the enormous wheel that represents the screamer with its 100-foot radius. Now, what's really important is that they mention, I'm going to go and highlight this a little bit here, they're saying that half the wheel is below ground level in a very dark, murky pit with water at the bottom, which leads us to believe that half of the wheel is above ground. So we actually have kind of a diagram of this where half of the screamer is below, half of the screamer is above. That's going to play a pretty important role when finding our mathematical connection here. As the screamer rotates at dizzying speeds, riders flip into the air before plunging down and all that stuff. So they're constantly going from above ground to below ground. It says, Renee and Antonio wait impatiently to get on the ride, watching passengers load and unload. New passengers get on and strap themselves in as others emerge from a pit looking queasy. It says here, the wheel rotates 15 degrees to load and unload the next set of riders. So this 15 degrees is going to be pretty important. Renee's going to strap himself in. We're going to, ride this wheel here. So it says, this is just a bunch of exposition here that they're underground. We don't need to worry about this last paragraph here. It says, your task. Write a function that describes how far above or below the platform a rider is when the screamer breaks down. Okay, so in order to do this, before we start graphing, let's go ahead and try and understand the motion of this wheel known as the screamer. It says notch to turn, and I'm going to presume for a second that these people are going to enter the ride from right here. So this ride is going to be cycling counterclockwise in order to get to its destination. So I'm going to pause real quick. I'm going to blow up this wheel, and we're going to figure out just how we can find out where these people are. So give me a second. And we are back. This is our wheel that is meant to represent the screamer. Now from here, I'm gonna just draw our attention to a couple things. First thing is that the screamer is a wheel that has a 100-foot radius, but I'm not gonna make everything worth 100. What I'm gonna do instead is I'm going to go ahead and just scale everything down to 1. So everything's gonna get scaled down or divided by 100, so it's all 1. That's why this coordinate at ground level when you presumably board the screamer is 1, 0. Hopefully that makes some sense. Now, if you look at each of these notches is meant to represent 15 degrees. If you went 15, 30, 45, 60, 75, 90, that would make sense if you notched your way up. And so from here, let's go ahead and write that down. We're going to write down 15, 30, 45, 60, 75, 90. Again, approaching in 15 degree increments. Now, I'm not going to worry about any of these other values on the left side or on the bottom left or on the bottom right of the screamer. For now, I'm just going to go and preface this with, I just need you to trust me. The 75 and the 15 aren't going to matter. We're not going to worry about those. We'll have eventually a way to deal with them, but realistically, we're going to work on the 30, the 45, and the 60. Now, there's a reason for this. And that is because, give me 1 second, let me paste this next image in. And we are back with the next image. Now you might be wondering, what does this image here on the right side have anything to do with this Ferris wheel? Well, remember, our objective is to find out how high off the ground we are from the screamer here. And so hopefully it makes sense as to why each of these triangles, I am only going to be measuring its vertical side. In other words, its height. Now, if I was to draw the screamer here, if I was to go to 30 degrees, my height from the ground would be a vertical line going downward. If I was to go from 45 degrees, I'd connect here with my radius and go downward vertically. The reason why that's important is because I have now drawn a couple of shapes that I'm hoping you would recognize. These shapes here in red are right triangles, just like the ones here on the right side of the diagram. And specifically, again, notice I got rid of the 75 and the 15 because those types of right triangles have angles that I'm not too familiar with. However, I do know the 30, the 45, and the 60 because these are our old buddies, our special right triangles from Integrated 2. So if I'm going to make the radius 1, that means that effectively the hypotenuse of each of these triangles is 1, as listed on this diagram right here. So using our knowledge of special right triangles, we can say that on a 30, 60, 90, if the hypotenuse is 1, opposite the 30 degrees, and feel free to pause if you think you want to try and beat me to the answer to this problem, that's going to be 1/2 tall. Opposite the 45, to get from 1 back down to a leg, that's going to be 1 divided by rad 2. After some rationalization of the denominator, I'm going to get rad 2 over 2. And then opposite the 1, this guy would be 30 degrees, this red angle, which would make him 30. Making him 1/2, not 30. And then this question mark will be 1/2 times rad 3, or rad 3 over 2. Again, what am I paying attention to? I'm only paying attention to the heights. We're not going to worry about our lateral distance from the center of the ride for now. That will be in the next lesson. But again, we're just looking at heights right now. So let's find out how that translates into this circle. Well, from here at 30, since my height is 1/2, and if you looked at this almost like a coordinate plane, you could see yourself possibly making coordinates here of something comma something. Now again, we don't know the lateral distance, but we do know the vertical distance. So I know that that's something comma 1/2. Hopefully you were able to discern that from this 45, you would have something comma rad 2 over 2. And then from this 60, you would have something comma rad 3 over 2. This 90 here would be something, 0 comma 1, right? If this is 1 comma 0. This 180 here is going to be negative 1 comma 0 because it's the same distance to the right as it is to the left. And then of course this 270 is going to be 0 comma negative 1 because we're opposite the 0 comma 1. And again, all of that is because the radius is 1 foot. Okay, I'm going to go ahead and pause and come back to the next bit. Give me a second. So I'm hoping that by now you will have realized that we're dealing with a circle. And that means that circles with their symmetric physiology, you can determine that with the 75 and the 15 being marked off, you can ignore these angles with this circle. Now, this 30 is going to have a symmetric buddy on the other side. Okay? Notice how you have 180. Notice how you have 30. If you go from 0 to 30, you're arcing 30 degrees up, which means you're going to backtrack arc 30 degrees up from 180, making him 150. You moved forward 45 degrees, you're going to move backwards 45 degrees from 180, so 180 minus 35 is going to be 135. And then again, upwards of 60, backwards of 60, that's going to make this guy 120 degrees. And then we'll go ahead and do the same thing, but forward. We'll go ahead and go to 180, and instead of going back 30, we'll go forward 30 more. So 180 plus 30 is going to be 210. 180 plus 45 is going to be 225. 180 plus 60 is going to be 240. And then again, the way to get these guys is I'm going to go all the way to 360. I'm going to backtrack 60. So 360 minus 60 is 300. 360 minus 45 is going to be 315. 360 minus 30 is going to be 330. So what we've just found is we've just found all of our angles on this Screamer Ferris wheel here. Okay. Now, again, we talked about symmetry a little while ago. Hopefully it makes sense that at the 30-degree counterparts, we're going to have something comma 1/2. At the 45-degree counterparts, we'll have something comma rad 2 over 2. And at the 120, we'll have something, something comma rad 3 over 2. I'm going to go and take a second and fill in the rest of this. This is going to be negative 1, 0. The 210 is 30 degrees off the axis, so it's going to be the equivalent of 60 and 150. And it will be something comma 1/2. That's 1 over 2. Something comma rad 2 over 2. Something comma rad 3 over 2. Again, going to 300, that's going to be something rad 3 over 2. And then finally, something comma 1/2. So I hope everyone's okay with this. Again, what are we finding? We're finding the heights of the seat on the screamer at any angle on the screamer. So only one thing to change now, and that is the signs. Notice how they said the screamer goes underground for part of it. That should happen right here where this blue line happens. Now underneath ground, hopefully it makes sense that your elevation is negative. So all of these guys on bottom should all be negative values. So that's what we have right now. We'll come back to it in a little bit after I do the next activity, and we'll figure out exactly what we've just done. I'll be right back. And we are back for the second half of this problem. So after determining all of the individual heights of the chair on the Ferris wheel, again, as dictated by this circle right here, what we're going to do is we're going to translate all of those heights onto this table of values here. So notice how all of the degrees are parsed out by 15 degrees. And so we will then figure out the height of the chair at that point in time. So let's go and do that. Well, first off, remember how I told you before, we're going to ignore all of like these non-special right triangle values. We're just not really going to worry about them right now. Eventually down the line, we will have a means to deal with them, but we're just not really quite there yet. And so, yeah, we're just going to kind of disregard them for a little bit. And that's my last guy. Okay, so we don't have to worry about them. And so now what we're going to do is we're really just going to translate all of these heights into this table, and then we'll go and do that. So hopefully it makes sense that the scaled height would be 0. And then the 30 degree will be 1/2 or 0.5. This will be rad 2 over 2, and the 60 will be rad 3 over 2. The 120 will once again be rad 3 over 2, 135 will be rad 2 over 2, and then 150 will be 1/2. 180 will be back to 0. Again, I'm just pulling these answers from this circle here. More importantly, I'm pulling them from the y coordinates of these coordinates here on that circle. And then remember, once we pass 180, it says that the screamer goes underground. And so what we have here is we have the same repeats. So it's going to be 1/2 rad 2 over 2 and rad 3 over 2, but they are all negative, like we said in the previous little bit. That's going to be negative 1. Let's see here. This is going to be negative rad 3 over 2, negative rad 2 over 2, and negative 1/2. And then at 360, we'll be back to 0. There's not really a need to worry about the actual height of the platform, just because that's more of like a metaphor for this problem, so we don't need to really be worried about that. I'm more worried about these particular values here in this table, so if you need to, pause the video, get caught up. I'm going to go ahead and go and grab the next part of this lesson. Give me 1 second. And we are back. And so now this is going to be one of the only times in this class where I actually ask you to graph with a reasonable degree of precision. And so what I'm going to do is I'm going to go ahead and I'm going to go and change my brush size down a little bit because I want this to be like really, really thin. And so let's see, how thin is this? That's really thin. Okay, that's great. All right, so from here, I'm going to go ahead and space this out in a very particular way. So just kind of bear with me here. Obviously, this here is 0, and then 0, 0, and then these are all my x values. All my input values are going horizontally. All my output values are going vertically. Let's talk about what input and output actually are in this case, though. If we go back to the circle, notice how we had to input a degree, and then we got out a value. Again, we input a degree. The degree is what caused the value to happen. So we can hopefully assume from there that the input, or the x-axis, are the degrees. And then the height of the chair is the actual height, for lack of a better word here. And so hopefully that makes sense that we're inputting the angle, we are getting out the height. And so now that means that I'm going to go and make the 30, 45, 60. All that stuff is going to be, all the 180, all the 315, all those degrees are going to be on the x-axis. All the heights are going to be on the y-axis. So I'm going to do this in a very particular way. It's not going to make a whole lot of sense right now until I explain the next couple of lessons. But for now, we're going to treat each tick mark as 15 degrees, meaning I'm going to skip the first tick mark and make him worth 30. And my handwriting is going to be a little hard to read here. That's going to be a 45, and that's going to be a 60. And now I'm going to go ahead and pause. Oh, actually, not yet. I'm going to skip another space because I'm going to skip 75, and that's going to be 90. So notice how in between each of the intervals of 3, I skip 1 because that's the angle that I don't care about. And then I'm going to go to 90. So I'm going to pause real quick now, and I'm going to go and fill in the rest without wasting a whole lot of time. Give me a second. And I am now back with all of these values here that I've uploaded. And so now what I'm going to do is I'm going to take a look at what my range is. Now from here, I totally forgot to fill in 90 here. It seems like that's actually supposed to be 1, and I got that from the circle. If you look at the range of the values of the y, the biggest value I get is 1, and the lowest value I get is -1, with 0 being in the center. So why does that help me? It helps me figure out how far up and how far down this graph is going to go. And so here's something I just need you to trust me on. And again, this is the leap of faith that I need you to take. And that is that at 60 degrees, that's going to be approximately 1 unit. And without understanding the next couple of lessons, you won't get that, but just trust me, it'll make sense later. So I'm going to count 1, 2, 3, 4 boxes to 60, which means I'm going to go 1, 2, 3, 4 boxes to 1. And then 1, 2, 3, 4 boxes down to -1, and that's going to be the range of this graph. Again, you don't know why that's happening, but it's just happening. Okay, so now I'm going to go and expand the brush size just a little bit, make it a little bit bigger. And so now what I'm going to do here is I'm going to start graphing these points here. So I'm going to do this with a reasonable degree of accuracy. At 0, I get 0. At 90, I get 1. Now, in between those 2 points, there actually is a number that really gets me something clean. And that number is 30 degrees because it gets me 1/2. I'm going to go to 30, 1/2, and fill in the dot there. And I'm going to label that 30, 0.5, or 1/2, depending on what you want. Now, I'm going to connect those guys in an arc because remember, this is a circular function, right? As we spin upwards through the screamer over here, we circle our way upwards. So hopefully it makes sense that we arc up in a circular way. Now between 90 and 180, 180 is an easy culprit because he gets me 0, but 150 also gets me 1/2. So I'm going to go and put him at the same elevation. I'm not going to label him. I'm just going to go ahead and call him 1/2 in the same position. Then between 180 and 270, 270 gets me -1, so I'll go and slam that point down here, right? 270 gets me -1. And then from here, the 210 gets me -1/2, so I'm going to put him here. So notice how I'm looking for all of the easy points on this thing. And then between 270 and 360, the 330 gets me -1/2, 360 gets me 0, and I'm going to go ahead and arc him just a little bit like that. And now notice how this accounts for the screamer spinning counterclockwise, but let's say there was a malfunction. In fact, the screamer could spin clockwise, and that means I want you to put a little bit of a tail in the back, shooting downward. Okay, let's go ahead and talk domain and range for this thing. The domain is going way to the left and way to the right with no jumps. That means that this domain is going to be the set of x. The set of x such that x is an element of all real numbers. The range is locked between -1 and 1, so the set of y such that y is in between -1 and 1. And we still haven't figured out the equation for this periodic function. And so this periodic function here, let's take a look at it. Well, there was a point in this problem here that I asked you guys to ignore, and it asked you for this. It gave you a triangle, and it gave you a theta, and it gave you a y, and it gave you a 1. And it said, in general, what is the relationship that you see? Well, if we looked at sine of theta, right, because we have opposite of our hypotenuse, that would get me y over 1. In other words, y equals sine theta. We input the degree, we output the height. And so that ends up being the equation of this function, y equals sine of theta. Hopefully that makes a little bit of sense. One last thing I want to go over is something called period. Period, and I'll go and define this for you guys here. Period, let me go ahead and switch up the text. Okay, cool. Period is how long it takes for a function's behavior to repeat. So if we're looking at repetitive behavior, notice what's happening at the origin. You are intersecting the x-axis moving upwards. The next time that happens is actually at 360, right? So notice the upward motion here of the graph crossing the x-axis. That means that the period of this thing is 360 degrees. So welcome aboard, everybody, to the first periodic function you're going to learn, and welcome aboard to the introduction to trigonometry. This is an image you're going to want to get used to. We're going to learn more about this circle as we move forward, but hopefully the Screamer kind of gave you a little bit of an intro with a bit of a game kind of twist on it. And so, as always, leave questions or comments in the comments area. That will wrap it up for the first trig lesson. I will see you all in the next episode.